Talk about the atmosphere, air pressure, and wind. The atmosphere is a whole layer of air that surrounds the Earth, and it is very small. In this picture here, you can see this incredibly small sliver of blue next to this huge area of Earth. That little sliver of blue is our atmosphere. It is very small. If the solid part of the Earth were the size of a peach, the atmosphere would be no thicker than the peach fuzz. Now, one thing about this atmosphere is that the air becomes thinner the farther down you go, farther up you go. Let's imagine this right here is the atmosphere. You can see from this diagram that all the little molecules of air are down here close to the Earth. It's gravity which is pulling molecules of air down. And as a result, 99% of the atmosphere mass is going to be in the bottom 20 miles of closest to the Earth. And the 20 miles closest to the Earth has 99% of the mass. It's all gravity is what it turns out to be. So if you're standing here, see my very unique little stick figure. If you're standing here and take a deep breath, you're getting a lot of air molecules. But if you happen to be on a mountain, now mountains are not going to extend very much past this, but say you were on a mountain that's way up here and you were to take a deep breath in, then you would not get near as many air molecules. Sometimes people who are on top of mountains like Mount Everest have to wear an oxygen mask. Now, there is no definite line separating the atmosphere and space. Space up here is the absence of an atmosphere, and you can see the space that happens to be right here. That's space, and it looks like there's a lot of blue down close to the Earth, but you can see it kind of gets a little bit fuzzy when you get up here. That's because all the mass of the atmosphere is this heavier, this blue right here, but right here you have kind of the fuzzy blue. So you can't just jump into no space and then space. You have space that kind of starts within this area here. In fact, you can kind of see a little bit of the black that creeps up toward the Earth right through here. There's no definite line in which it is separate. Let's take a look at what is in our air. We have 78% nitrogen, and that's not what you might expect. I think most people expect the oxygen to be what is predominantly in our air. But oxygen is only 21% of the air that we breathe in. And we do have 1% of things like carbon dioxide and argon and so on. Let's talk about air pressure. Air pressure is the force of air molecules pushing on an area. Let's say you're standing here. You have at the bottom of a mountain a lot of air which is pushing down on you, and that is registered in what's called the air pressure. Here you have something that's registered in MBs, which is millibars. 1008 is the reading there. Here, a little bit higher on the mountain, you don't have quite as much pressure coming down on you. They have something called 915 millibars here. Here you have at the top of the mountain even less air pressure, and it looks like it's a smaller number, 840 millibars. If you ever open a can of tennis balls, you may realize that whenever you open it up, you hear air rushing into it, psst, kind of a hissing sound. And what's happening is the tennis balls are vacuum sealed. They don't have any air in them. So what you basically have is high air pressure rushing into low air pressure. It's kind of like taking a bowl of Cheerios. And if in your bowl of Cheerios you have a divider in between, and on one side you have all the Cheerios basically, and I won't have enough time to draw dozens and dozens of Cheerios here, but if you just had maybe one or two Cheerios on this side, once you lift this divider, what's going to happen? The Cheerios are going to divide out. They're just going to kind of be spread out throughout the bowl. Same thing's going to happen here. You have a lot of air pressure outside the can and no air pressure inside the can. So once the barrier is released, it kind of evens out. You have high that comes in to the low air pressure, and that's actually going to be important when we start talking about wind. Now, I mentioned down here that we have readings in millibars. Those readings come from a barometer. Now here we have two examples of barometers. This is kind of an older fashioned aneroid barometer where you have air pressure which is pushing down here on this sensitive aneroid cell, and as it pushes down the reading goes up. Here's probably more like what you see today. This is liquid mercury down in the bottom here, and whenever you have the pressure pushing down on it, that pushes the mercury up into the reading right there. Okay, so let's go to a couple of other things. I'm going to get to that in a little bit. Oh yeah, here's millibars. And I'll open this up a little wider here first and move some of these out of the way. But you can see, and it's not very clear, I apologize for that, but you can see you have millibar readings. You have 996 right here in the center. You have then a little bit bigger, 1,000, then 1,004 and 1,008. And this is not like you really see it, but this is kind of to prove the point here. What happens is whenever you talk about wind, the wind is going to travel in a predictable direction. And weathermen can tell you which direction the wind is traveling just by looking at maps such as this. Wind always travels from high pressure to low pressure. You may remember the bowl of Cheerios that we talked about, and if you take out the partition, you have the Cheerios that are where it is high concentration of Cheerios flooding to the area where it's low concentration of Cheerios. Same thing with wind. Here at this 1,008 you have high concentration of air, and at 996 you have a low concentration of air. So the wind goes from high to low, and that's the direction the wind would travel if you have these readings. Now notice on the other side of the country it's opposite. You have 1,008, 1,004 over here. It's all traveling from high to low. So in one side of the country it's traveling in one direction, another side it's traveling in the other, but it's always going to be from high to low. Now let's take a look at what the millibars would more likely look like here on Earth, and I suppose I should erase a thing or two. Here's what a weatherman would more likely see whenever they look at the readings. Now here you have lots and lots of lines, but you can still figure out what's going on. You have, let's look in the middle. You have 1,025 here. Down over here you have 1,005. So this 1,005 rushes up toward the 1,025. Here you have, let's take a look over here. You have 1,021. You have 1,016. You have 1,000, oh my bad, I said it wrong over here. It goes from high to low. So you would have all the air pressure going that direction, from high to low. So from 1,025 toward the 1,005. Here you have 1,021 toward the 1,016 and whatever that says there. So it's always going from high to low. I say we have 1,020 to 1,010. Probably have some lower readings up along the coast. Look here, 1,019 all the way down to 1,006, 1,001. So lots of different direction wind will be going on any given basis, on any given day. Now let's take a look at here in Georgia. And I figure I'll probably have to erase these as well, but that's okay. So let's take a look here in Georgia. Now this is not today, but this is just any given day, you might say. You have 1,018 here, 1,014 here, and you see the pattern all the way to 1,011 here. So it goes from high to low. Do you really have much of anything going on right here? No. You have 1,017, 1,016, 1,017, 1,016. Probably not much wind in this area. But where you have the higher to the lower, that's the direction that the breeze is going to travel. Hopefully that makes sense to you. Now let's take a look at this. This is kind of an important concept. This talks about unequal heating. You know, I said that air pressure moves from high to low. Now, what causes different air pressure in different places? We already said that at the top of a mountain you have lower air pressure than and at the bottom of the mountain. So you sometimes get breezes going up to the top. But what about here in a flat field? Here we have a flat field. It could even be a flat state. I mean, miles and miles long. Here's kind of a crude way of me explaining this, and hopefully this will explain it. Here we have the sun. The sun shines down on the ground. It heats up the air near the ground. You follow me? Hot ground, hot air near it. What happens to hot air? It rises. So if you have hot air which is going up, that's acting as a buffer against the air pressure. And I'll just abbreviate it as AP. You know, the air pressure is constantly going down on things onto the earth. So you have lower air pressure here because you have that hot air that is rising. Let's try to put that in a different color. You have lower air pressure here because you have that hot air that is rising. Now let's use this for an example here. Now I just have one cloud. Probably wouldn't affect as much with just one cloud here. But let's say you had a bunch of clouds. The sun is not going to be quite as hot on this land, which means the air around it is going to be not quite as hot either. Yes, you will have some hot air rising, but not quite as much. So the air pressure that is coming down is not going to have as much of a buffer against it. So in an area like this, you would have higher air pressure. Higher because there's not much hot air to stop the air pressure. So you see what you have. You have higher air pressure in one place and lower air pressure in another. And you know what happens. Winds go high to low pressure. So that is how this happens. And it all has to do with unequal heating. Unequal heating. You don't have the same temperature. You don't have the same heating in all places on the earth. In fact, in different areas of the state, you'll have different heating. You will have unequal heating. So that is why you have wind whenever you have unequal heating. Well, I hope you've learned a little bit about the weather and atmosphere.